Okay, continuing our discussion, wrapping up our discussion about the E2 elimination is to figure out when can we predict that an E2 reaction is going to happen? When is that mechanism favored? And it turns out that and many times the E2 is competing with the other bimolecular reaction that we encounter, the Sn2. So let's talk about the E2 versus the Sn2. So Sn2 backside attack. What does the Sn2 mechanism require? Well, it needs a strong nucleophile. It needs a strong nucleophile to do that backside attack and displacement replacement. And the other thing that we know about the Sn2 is that steric hindrance is something that really slows it down. So steric hindrance is bad. That is bad news because you're not going to be able to get into that backside to do the substitution. Okay, so what are the requirements of the E2 elimination? This is something that needs a strong base. It needs a strong base. Remember, this is the bimolecular reaction where it attacks the beta proton, forms a pi bond, kicks off the leaving group. So I need a really strong base for this. And it turns out that the rate is not affected by sterics. So really, a lot of times it's going to be the sterics that's going to distinguish, determine the path of E2 versus Sn2. Okay, so, and when do they compete? When is it that we're looking at this competition? When our reaction conditions either contain HO minus, which is hydroxide, or RO minus, some carbon group with an O minus, that's called alkoxide. Why? Because these are both strong nucleophiles, meaning they can do the Sn2 backside attack, and strong bases, meaning it could do the E2. So as soon as we see in our reaction conditions that we have either hydroxide or alkoxide, we have to be on the alert that we're going to get a bimolecular reaction. It's going to attack something. We just have to determine where is it going to attack. Is it going to attack the backside of the carbon bearing the leaving group, or is it going to attack the beta position, the proton on the beta hydrogen, and hydrogen on the beta carbon, and do an E2 elimination instead. So let's look at some data. Let's see. So if we were to study this reaction, we could maybe take a variety of alkyl halides, a wide variety of alkyl halides, and test it. Let's react it with ETONA. What does that stand for? That is that sodium, of course, tells me that I have an ethyl O minus. So that's called ethoxide. That's called ethoxide. So this compound is called sodium ethoxide. And so that fits one of our situations here, our characteristics where, yes, it can be a strong nucleophile. If it was a nucleophile, what would the reaction look like? That's a substitution reaction. Sn2 means instead of the halide, I would have an methoxy group, an ethoxy group attached at that position, backside attack. So I can get an Sn2 product here, or I can get some kind of alkene. Of course, the structure of the alkene depends on what my carbon group looks like here, and that would be the E2. So we can actually run the reaction and isolate the products and quantify it, measure, see how much of each product we have, and we can draw some conclusions from that. Okay, so let's take a look at the series of halides that we're going to use to study this reaction. So the first one is just I could have the bromine leaving group on just a methyl group, right? So we could abbreviate this MEBR, just kind of getting us used to some of these abbreviations that are used for certain groups like the methyl group. And I could classify that halide as being a methyl halide. In other words, it's just on a methyl group. Okay, the next one has a 4-carbon chain, 1, 2, 3, 4. They're all in a straight line and straight chain, and I've attached the bromine at the end carbon. That's just the normal type of butyl group. So this could be called N-butyl bromide. The N-butyl group is shown there. And what kind of carbon? How would you describe the carbon bearing the leaving group in this case? It has just one carbon group attached. So this would be an example of a primary alkyl halide, right? Here we're describing the carbon type of the alkyl halide, type of the leaving group. Or we could actually describe that as well instead. What kind of carbon is the leaving group on? Okay, how about our next one? This is now we have a branched 3-carbon chain and another CH2 that is described as the isobutyl group. So IBU is a way to abbreviate isobutyl. So this is isobutyl bromide. This is still a primary leaving group. This is still has just one group attached. Okay, but now I have, you know, the group, instead of a straight chain, I have a branched chain. So we're going to see if that affects the rate at all. Okay, this next one, what would this has another common name. Do you recognize this 3-carbon chain? When you have 3 carbons and you're attached at the middle carbon, this is called the isopropyl group. So this is isopropyl bromide. This is now an example of a secondary leaving group. And finally, what do we have here? 4 carbons. Our carbon where the leaving group is has 3 methyl groups attached. That's called the tert-butyl group, tert-butyl bromide. And why is it called the tert-butyl group, the tertiary butyl group? Because it is a tertiary, the point of attachment is at a tertiary center. That's why it has that name. Okay, so what we're doing as we look at this series of compounds, why was this series of compounds chosen? Because they are we are increasing sterics as we move from one to the next. We're increasing sterics here. Okay, and the way we could describe this isobutyl group is we have some branching, but it's not branching at the carbon bearing the leaving group, the alpha carbon. The branching is occurring at the beta leaving group. So we could describe this as beta branching. So that actually distinguishes these 2 primary substrates. One has no branching and one has branching taking place at the beta position. Okay, so when we run these reactions and we see what's happening, let's take a look at the data. When we have a methyl bromide, methyl bromide, does that look good for backside attack? That looks fantastic for backside attack. So actually we get 100% Sn2 because what do you think about doing the E2 elimination on this? If you try to do the E2 mechanism on this, what would be the problem? When you try and attack that beta proton, you see, well, wait a minute, there is no beta carbon, so there can't be a beta proton. So this is actually not even applicable. It's impossible to form a carbon-carbon double bond if you have no if you only have 1 carbon, right? So there's no beta hydrogen. So this is E2 is not even an option there. Okay, but when we get to primary now, we can have both substitution and elimination. But because it's primary and there's no sterics, we get primarily Sn2. We get majority of that, maybe 90-10. So some elimination happens where you get the double bond here, right? That's what elimination means. You get the double bond, but primarily you get Sn2. But as soon as we start to make that a kind of a bulky group that's attached and we increase the sterics, all of a sudden it's almost 50-50 and even favoring the elimination. Super sensitive to sterics. So that really starts to slow down the Sn2. And if you're slowing down the Sn2, then the E2 takes over. Okay, and when we jump to secondary, it actually goes all the way to the other direction now where it's 20-80. So E2 is favored. And then when we get to tertiary, how does backside attack look? How does backside attack look on a tertiary center? Remember, we said that Sn2 is so slow on tertiary, we actually describe it as no reaction. So let's say we have 0% Sn2 because with a tertiary alkyl halide, tertiary RX, there's no reaction with Sn2. There's no reaction, no backside attack is going to take place. So in that case, a reaction does happen. So back when all we knew about was the Sn2 mechanism, we'd say, oh, no reaction. But now, because there's a competing reaction, there's another path that can be taken. That actually is what happens. We get E2 elimination. We get the alkene product. Okay, so what's the turning point here for E2 versus SN2? Looks like E2, E2 wins, unless it's not possible, unless it's primary. Primary is the only time SN2 is going to win. And even when we get to secondary here, we want to point out that with the secondary alkyl halide, E2 wins. So in this E2 versus SN2 competition, it typically goes to E2. That's the winner. All right. So why is that? Let's take a look again. Let's look at something like T-butyl bromide. I've drawn out T-butyl bromide here. Oh, I see a typo in my notes. I'm very sorry. I think that perhaps this was something that happened with my let me just cross it out, make it easier that way. When I created the PDF, something maybe, I don't know what happened there. Sorry. So there should be a leaving group in that position. And this is a tertiary center, right? This carbon has 3 carbon groups attached. So when my ethoxide is coming in, and you think about the different places now, it has 2 different sites it can attack. If it wanted to do the backside attack, that means it's coming in and attacking at this carbon, but that now is so hindered because of these those methyl groups. It makes it super slow. So this does not happen. So why does E2 possible? Because for E2, all it has to do is come out and grab this beta proton. Protons are always accessible because they're easier to get to than the tetrahedral carbon atom, and so that is okay. So eliminations, E2 is not affected by sterics. The rate we're looking at it winning completely over when we have a tertiary center. Okay, so let's just put that in writing, what we just observed here. Backside attack when we have a tertiary, right? This is a tertiary alkyl halide. RBR, we have a specific one here. When we have a tertiary leaving group, let's even more simply say we have a tertiary leaving group. When there's a tertiary leaving group, the backside attack is too hindered. Backside attack is too hindered, and but the beta proton is more accessible. Okay, so we get 100% E2 if we have a tertiary leaving group. 100% E2. Okay, what else could we do? What if we varied the base that was coming in? Would that have an impact on the E2 versus SN2? It certainly would. So let's look at 2 choices here. So we're keeping our substrate the same. We have, looking back at the N-butyl bromide, which we saw up here, gave primarily the SN2 mechanism. So if we use a base like methoxide, so this is, we could write this as MEONA. Is another way we could write this. This is called methoxide. So if we use methoxide, or we use TBUOK, so we could draw that out. That would be TBUOK, or that's called tert butoxide, or T-butoxide is how we would describe that base. So so is there a difference in our product distribution? There certainly is. If we use a normal base, a base that is not bulky, once again we get almost exclusively SN2, maybe just a smidge of elimination. So what's the rest of it? Maybe just didn't react. So 96% conversion to the substitution product. And again, let's point out now here we are again increasing the sterics. This time we're doing it by using different bases. So when we use a bulky base to come in, even though this is primary, right? This is a primary leaving group. If the base that's coming in is bringing some crowding, that again slows down that backside attack, and we can favor it to be E2 elimination. So if you really wanted to do an E2 elimination, you could use a bulky base on a primary to make that happen. All right, so t-butoxide, we described t-butoxide as a bulky base. Okay, what are some other bulky bases? We could use amines, triethylamine here. If we take a look at this first structure, so we have a nitrogen with 3 ethyl groups on it. So when you take a look at that, that kind of looks like t-butoxide, right? Even bulkier because it has ethyl groups. And so this is super, super bulky. And that's going to be something that would also favor the E2 conditions. And diisopropylamine, the next one over there, IPR2NH. So that is a nitrogen with 2 isopropyl groups. So again, super, super bulky. Those amines. Remember, amines love doing the SN2, love doing backside attack. But if the amine you're using is very crowded, like a tertiary amine here has 3 carbon groups, or one like has 2 isopropyl groups, those are going to be very, very difficult to do backside attack. Very difficult to do backside attack because it has too much steric. So these are kind of classic E2 reaction conditions, is using a bulky base. Okay, if you have a choice of one position or another to do that regiochemistry, remember Hoffman product is what's going to be favored, because we're going to get the less substituted. That means we get the less substituted alkene. That's the opposite of the Zaitsev's rule, says you get the most substituted alkene. When we use a bulky base like t-butoxide or one of these others, we would get a less substituted alkene. We call that Hoffman elimination. You'll see in the Klein text, it uses a few other bulky bases. DBU, DBN has the structures for those. I'll never use those. In fact, when I anytime I want to use a bulky base, I always use t-butoxide. So we know what to expect. I just wanted to point out that there's some other options that we can have. Okay, what else can we do to favor elimination? One other thing we could do to favor elimination is we can add heat. Addition of heat always favors elimination because we get an increase in entropy. Elimination reactions cause an increase in entropy because we're losing our leaving group, making an alkene and a leaving group. And so we are increasing the number of species that we have, chemical species. And so because our delta S is positive, then if you increase the delta T, increase the temperature, you increase this component of the Gibbs equation. And so you that is something that also makes eliminations more favorable. So a lot of times you'll see heat thrown in there to give us an extra hint that it's going to be an elimination. Okay, so just to summarize, our preference for E2 over the SN2 by the alkyl halide type. Okay, when the one that prefers E2 the most is a tertiary alkyl halide. This is going to be exclusively E2, about 100% E2. Okay, and when we go to a secondary leaving group, E2 favored, E2 wins, E2 wins. Okay, but then when the tide changes when we move to primary, when we're looking at primary, we're getting about, not 100%, but mostly SN2, mostly SN2. Okay, and I'm not even going to put methyl on the list here because methyl is not ever going to do an E2 elimination because it has no beta hydrogens. So primary, secondary, tertiary. If we have a primary substrate, we're expecting SN2 to happen. If we have a tertiary substrate, we know that the E2 is going to happen. And the key here is to recognize that even with a secondary, the secondary is also, when we look at that data, the secondary is also included down here, sorry, with the E2 being favored. Okay, let's